to do this in your head, and let me talk about the whole math thing. So, in the end, that May date where we take our exam, you will have a multiple choice and you'll have pre-response, just like you'll have for every single test for me. I try to mimic what I can for the AP exam, so it's a piece of cake when you get there. The real struggle is just the mental part of like going 3 hours and change of chemistry. That's the hardest part at the end of the day, okay? But normally I would say multiple choice, no calculator, okay? Because on the AP exam, multiple choice, you don't get calculator. I went through the test last night and I took it again and I was like, okay, there's more math on here than I thought I had on my Unit 1 test, so I will let you use your calculator on your Unit 1 test. But after that, we're going to try to do all mental math. Not all, like free response, we absolutely have to use calculator because we'll have some really, weird numbers that we can't quite mentally maybe take percentages of and calculate and kind of guesstimate. But on multiple choice, they try to give you numbers that you can work with in your head. So like, for example, look up here for me. What I'll say is like, take 4.4 grams of carbon dioxide to moles. What's the molar mass of carbon dioxide? Carbon dioxide total? It's 44, right? And you could take 12 plus 16 in your head. You could do that, and that's 44. So 1 mole.
Teachers, students from bus 124 just arrived on the campus. Please do not count their target.
What's 4.4 divided by 44? So 4.4 is what percent of 44? So 0.1. So it's going to be so it's 10%. So that's 0.1 moles. So then we could then from here do a mole ratio, say 2 to 1, and then we get 0.2 moles, and then so forth. So they'll try to give you percentages of a whole, or something that's a little easier to work with, versus like, how many moles is 1,280 grams of carbon dioxide. That would be a little bit more difficult. So we'll work with that a lot more, and I'll have you guys do some mental math throughout the next unit. But I thought it would be unfair to tell you that today, with the test being Friday, and a quiz tomorrow. So the quiz has math on it, and your test has math. So in terms of the quiz, we'll start trying with no calculators, but if you have to go, you got to go with calculator, okay? So eventually, though, we will get to the point where we're calculator free, okay? All right, so let's look up here. You guys have your periodic table? Keep trying to use this one only because it doesn't have the names on them, and you should be comfortable-ish, maybe with 90% of them with other names. The ones we don't use too frequently are like the lengthenite and actinide series. You won't see those too frequently. All right, so number of protons. Let's talk about why you're saying the number you got, so we can all be clear on how we do this, okay? Margaret, can you tell me for silicon how many protons? 14. How do you know that from here? The bottom number is the number of protons, also known as the atomic number. Okay, so make sure the smart board's working here. All right, so this is our number of protons. Jillian, pick up from there. How did you get number of neutrons? Okay, so 35 minus 14 is what? 21 neutrons, okay? And then the 35, FYI, is what, Jillian? All right, so that's our mass number, or the atomic mass. We usually say atomic mass when it's the average, like the point blah, 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 but this is just a mass number. That's 14. And then in terms of electrons, Chase, how would you get that from the information given?
So,
I give you the hard one.
yeah, so since it's plus 4, and then we'd have 10 electrons, because we 3 more protons.
Or we'd have, 4 less, right?
Yeah.
So with a plus 4 charge, that means you lost 4 electrons. Remember, you never, ever, ever, ever change the protons. That's its identity. That is silicon's DNA, right? That's going to be giving us information about the identity. So what you do is you take the original protons. Original protons is 14. Originally, you had 14 electrons because that's a neutral silicon atom. But once you change your charge, it's because of loss or gain of electrons. So you lost, by nature of how it's now positive, you lost 4 electrons. So there's going to be 10 electrons remaining. Okay. So for fluorine, Darcy, pick up what's protons? 9, as is. Carrington, neutrons. So you did 18 minus 9, right? So that's 9 neutrons. And then Emily, electrons. So you took your 9, you saw a plus 1 charge, so you added 1 electron to your original, so that went from 9 to 10. Okay? Andrew, 10. Tell me the number of protons.
50.
So you can find it here, so you have the periodic table, right? So you find 10. It's in group what? What group is 10 in? 4, okay? And that's why 10 occasionally can form a 4 plus charge because it's in that group as well. So 50, thank you, 50 protons. JT, neutrons?
6 to 9.
So you took 119 as the mass minus 50?
Yeah.
So you guys are trying to maybe master this in your head as well, okay? Simple addition and subtraction. And then, Megan, electrons. Right, so since it's neutral, since there's no charge indicated here, neutrons equals, electrons equals protons. Okay, Miriam, cobalt. Just making sure, yep. So that's in our transition metal area, and this is going to give us information just by the nature of the atomic number being here. And then, William, can you pick up for neutrons there? Okay, so tell me what you did mathematically. Okay, so we're rounding our mass to 59 as a whole because we can't have a partial neutron, okay? Okay, and we got 32. Is that 32? Yep, just make sure. Mental math, okay. So then, in terms of electrons, everybody? 27, because it's the same, because it's a neutral species. All right, krypton, so we got 36. Protons, how many electrons? Electrons? 36, because it's the same, right? It's a neutral compound, or atom, okay? And then we subtract, what do you get for your neutrons? 49 neutrons. Okay. So who feels a little bit better with subatomics? Okay, just doing a quick jump with that because you guys, I'll tell you the breakdown of the test and the quiz in a second. Now with this one, I just pulled some stuff from honors chem, so a lot of these things are going to be like the basics that you need to know, and then we'll apply like the mass spec on top of this. But for this example, you have 4 isotopes. If you guys can't see over there, I can make these numbers bigger. But the 4 isotopes all come in different relative abundances, which are given as percentages. How would we go about calculating average atomic mass? Do not say this out loud. Talk to your partner first. All right, you guys calculate the isotope, the first isotope, the 50. You guys, this whole area here, calculate the 52. This area here, calculate the 53. In the far area, calculate the 54. Yeah. If you can't see a number, let me know. No, please use a calculator. There ain't no way. Ain't no way. What's AMU stand for? Just making sure. Atomic mass units. And then 53.376. Alright, first group, what'd you guys get for yours? 2.1. Give me some extras. 5.6. Okay, I'm better with that. Next group? 550. Something like that. Okay, next group. 0.62.455. Okay, next group. Okay, just looking at these numbers, which isotope controls the average the most? The average would be the one that's most, or the average would be skewed by the one that's most abundant. So, looking at chromium on your periodic table, what's chromium's average atomic mass? 52.00, right? So it should hopefully, at the end, when you add these up, be what? Hoping 52.00. Let me add these up yet. 053, 7. Okay, so Enloe probably made up a percentage here, but we got close. So this is our average by inclusion of the relative abundances. Now, how could I make this an AP level question? Instead of giving you all this information, what could I do? The chart thing, mass spec, right? So how would that mass spec look if it were this and this information? So let's kind of draw a mass spec for this. What are the axes for the mass spec? Percent. I'm going to put percent/intensity because it's the hits that the detector is getting based on the isotopes that are flying at it. Okay, what goes on the bottom? Mass, and it's sometimes mass/charge because it's just telling you if it's an ion. These are not ions, or in this case, they're all atoms. So what would I have, or how many peaks would I have? 4 peaks, okay. And what would their sizes be?
Small, big, small.
Give me some. Which one has to be? Remember that the intensity peaks at 100, right? So that the one that's most abundant will be 100, and everything else will be scaled down based on that. So who gets the 100? 52. Okay, so we got a 50, 52, 53, and 54. So 50, 52, 53, and 54. 52 will be at the peak of 100, and then everything else is a fraction of that. So this one being 83% down to 4%, like that's nothing. That little boop right there is fine, okay? This one's like 10%-ish, so it's going to be about twice the size of that first peak. Boop. Okay, looking good. And then this one down here is even smaller. So my lines are actually taller than they, by the marking, are taller than they should be. So you just have to kind of do a relative marking, and you should be able to then, assumingly, take the percentages by normalization, and then go from there and calculate. Yeah.
If you had to draw it on like an exact graph, would you have to work backwards to find out where they would be?
You would never have to draw it on an exact graph because they want you to know the skill of taking the peaks to normalization by normalizing the percentages, right, to find your own average stomach mass. We never have to work that far backwards. It's just I want you to be able to recognize what the graph should look like and then understand the one that's at the 100 is the most abundant one. This bite is not 100%. Yeah, you'd have to work backwards by figuring out their normalizations by this, but that's too intricate. Okay, yeah.
If we are given a graph like that on the test, and we have to work out to find whatever.
Relative abundances?
Yeah. How exact will the graph be?
It'll give you 100 and a 50, and then maybe some little lines for you to give some estimation. But I have to take your data you pull off and calculate from there based on your estimations. Your estimations will still be within probably like 5% of what mine was. Okay, it'll be accurate enough to give you that. Okay, yeah. Just because that's how the detector reports the data out. Even though it's not 100%, because that would be the whole shebang. That's just how the detector reports it. Okay, and then let me tell you what's on the test first before I move on, because I want you guys to be able to focus your efforts today. Okay, so I'll write this on the board. Tomorrow your quiz is 22 questions. I have to give the answer to 23 because it's organic chemistry and we haven't talked about that yet. So quiz, I just broke it down. I don't mind telling you guys almost exactly what to expect. You should know what to expect. You should feel comfortable coming in tomorrow, or Friday and tomorrow, to be ready. Okay, so scientist, you watch the video on the history, and you probably go back and look at some of those. There's 3 questions there. Laws, and this is my kind of catch-all. Laws, naming, and then like just definitions, knowing the definitions of some terminology or rules about some terminology. There are 8 questions regarding that. That can be things like intensive, extensive properties, accuracy, precision, law of definite proportions, law of multiple proportions, things like that. Okay, I'm videoing too if you want this. Math spec, like we just talked about. 1, math conversions or percent composition, metric system prefixes like kilo to nano, things like that. 5, the atom, ions, subatomic particles, or isotopes, like what we just did. 4, and that's approximately what's on your quiz. Okay, so this is multiple choice. This is a great practice before your multiple choice on Friday. That's what I always do. I will always give you a multiple choice practice on the third or the day before the test, so you kind of know what to study. Okay, and then for your test, this is still kind of in limbo, but it's mostly still correct. For multiple choice, scientist, 3, not the same 3. Okay, but close. Laws and definitions, 7. Math, this is math spec, by the way, I'm sorry. Math is 10, combination of compositional stoichiometry, normal stoichiometry, no limiting reagent and multiple choice, percent composition, subatomic particles, isotopes, etc. is 8. There's an extra category for the multiple choice. There'll be labs, like things related to your math spec or your spec 20s, the kind of the concepts we learned about in the labs regarding crucible handling, cuvette handling. That's probably about it. There's 3 there, and that's it for the multiple choice. For free response, can I scroll down some? Yeah, for free response, you have 20 nomenclature, and it's split. 10 are formula to name, 10 are name to formula. Okay. There's 1 empirical formula, 1 molecular formula, 1 combustion analysis, 1, I try to do 1 of everything, okay? 1 normal, I say normal, meaning non-limiting reagent, normal reaction stoichiometry, 1 limiting reagent, and then 1 mass spec. So everything we talked about. I just thought I'd give you the details so that you can understand where most of your efforts should go within your studying habits. Okay? Any questions there, guys? Okay, so first thing we're going to do is I want you guys to first note there are some groups that have your same lab report. Okay, so you guys have already looked it over. You've kind of critiqued it. You have your rubric. I did not check to see if you guys put it on your Google Doc, but since we're keeping that entire lab on your Google Doc, if you have not, raise your hand if you did. If you put your analysis in your Google Doc, okay. Most of us did. We're good. But put everything in there. That way, when I give you guys your group grade, it's for the group there, and then we'll eventually print those out and put this in our lab minutes. So, lab group 1, raise your hand. Or lab report 1, raise your hand. Okay. You guys are going to get a 1 table in just a second. Lab report 2, raise your hand. Lab report 3, raise your hand. Okay. So some of you guys have other groups that are going to collaborate with you. Basically, I want you guys to spend less than 5 minutes sharing out about your critique, and then I'll make some extra commentary. But everybody in that big group has to say something meaningful, something worthwhile. So make sure you kind of divide up that, just 1 second, just so you can divide it up so everybody can talk about something here. I will say the correct percentage, I want to know what y'all's percentages were, but what were your percents that you calculated to be the bicarbonate of the overall mixture? Where'd you guys get? 93? 92? William, what'd you guys get? Okay, hold on. Another group? Yeah. 81?
91.8.
91.8, 81. All right, I want to know the rest of those by the end of the day, okay? So what you'll need to do is run your percent error from yours to what the true one is, which is 85%, okay? So I'll give you guys maybe 10 minutes right now to talk in the labs, and then we'll share out, and then you'll go back and you'll have time to work either studying or working in your lab groups if you need to finish up a lab, okay? So lab analysis first, go. Let's do lab group 1 and kind of this side over here, lab report 2 in the middle here, and lab report 3 over here. Here's my next one. I read it, So let me tell you what the flow of this is. I'm going to put a timer on for 5 minutes per group because I would like to make sure you have 30 minutes to review at the end of class, okay? So you're talking about general stuff like procedure, safety materials, data processing, how they recorded their data, and then talking about the greenness of their evaluation. And then if you can about atom economy, it's going to have to be if you remember what atom economy is. So basically address as many as their strengths and as many as their weaknesses as you can. You can also make some commentary on quality of reporting and such. Okay, so I'll add to that as we go. This is that rubric you guys had, so if you want to have that in your hand, you can. But I'm going to have the lab reports up here so everybody can kind of see and you guys can point to the things that are relevant based on what you're talking about, okay? So lab group 1, let's roll. And you guys can always scroll down if you need to, and the next slide has your rest of your data, okay? So, come on up, lab report 1. So 5 minutes, and I'll give you like the 2-minute warning, okay? I'll give you the 1-minute warning. So what I'd like for everybody else to do is just note some of the key points, because I expect that you guys will be writing your own lab reports. This should be like clear as day, right? So halfway close your computer so I know that you're paying attention to these lab reports. Is there a 5-minute question for you? Anybody can start?
Okay, well, one thing we noticed was they didn't give any procedures, but they did. Yeah. So we got no way of telling like what they used or how they went about measuring things.
I can go next. Kind of thing. It wasn't really organized. So one example was that they didn't have any listed materials in the lab.
And they also didn't have any safety procedures.
In their conclusion, they have a really good error analysis, but that's the only thing they have in their conclusion. They don't really have anything else of value besides the error analysis.
It's the arrow. Say that again, Marcus.
In their conclusion, the only information they really have are 2 really well explained error analysis. That's the only thing they really have. They don't have anything else describing like what they learned from it or if they learned anything from it.
What was so good about that error analysis?
They were very thorough about what they said. They were careful, or not careful. They talked exactly about 2 specific points. They could add in more things that they could have done wrong, but those 2 that they did add were really good.
So that would be a great example to utilize for our error analysis to note the direction of error once you guys do your percent calculations for some errors. Okay, next person.
As for the explanations of chemistry in the lab, it talks, oh gosh,
Use the scroll bar.
yeah. All right, it talks about how the moles of CO2 are equal to the moles of H2O because it's a mole ratio. And they used like this general concept to carry out all of their work. And even though they did it in a way that was kind of like unfamiliar to me, what they did like made sense for how they explained it.
Another thing when they were going to show their work, right in here, when they're looking for the mass loss, they just put grams, which is like a unit, but they didn't put grams of what, so it's very confusing to try to follow along with their work.
Going back to the conclusion, like Marcus was saying, they did really good error analysis. They pointed out, right here they said assumed, and they said assumed somewhere else, right here. which you're not really supposed to do in chemistry. You're supposed to be able to back up what you did with all your calculations and whatnot. And he's just saying, right here, he assumed that because of that, he knows what he was wrong.
And then for atom economy, when I calculated it, I got 63.08%.
How did you do that?
Well, the desired product would be the sodium carbonate. And then
Okay, so you carbonate what you wanted, and
right, and then but then in addition to that, you got carbon dioxide and water. So to calculate the atom economy, you'd have to do the desired over the total products, and when you do that and you multiply by 100, you get 63.08%.
From the atom economy in this procedure, we can deduct about what the lab did and how green it was and how efficient it was based on the percent. Like it's almost like percent yield of the stuff that you want compared to the total stuff. And so we found from teaching that 63% of the stuff we actually made was the stuff that we wanted, as opposed to being sodium carbonate.
However, for like our next concept, like dictating green, like how green it is, we talked about like reducing derivatives, and a derivative is basically like a parent compound that gives something else off. And additionally to the like sodium carbonate, you had carbonic acid, and that's not what you wanted out of it, so that's like a derivative, and almost like a fourth of your starting amount was carbonic acid, something that you didn't really need.
very nice. Okay, so you guys be loud as anything back here. You've got to speak louder up there. I'm not deaf, but I can't hear you. Okay, so good point on the air analysis. This one, the strongest point of this one, I think, was their conclusion in their air analysis. Their algebra that they followed through their math that Mark was talking about was wonderful. The labeling of identities of units would be even better. It is not how we solved it. We actually solved it in a much, I think, my process I showed you guys yesterday, which you guys picked up on, was simpler. But you'll notice there's probably 5 ways to solve a lot of these things. And I'll try to go with y'all's routes on some things, but my goal is always saving time too. Okay. And then they did have some careful wording in their error to try to say like they were sure or not sure. And then they had 2 trials. We always want to run 2 trials. We only ran 1 trial, unfortunately, just for time's sake. But we always want to run 2 or more. Good job, guys. Okay. Hit next for me, Cassie. Next button. Yeah. Thank you. The next, I think the next 2 pages are 2 pages there. Not the first 2.
Even out. Even out. Somewhere. Thank you.
So this was pretty miserable. Looked at this procedure and I was like, what is this? Heat mixture to a constant mass. You gotta explain everything that goes along with that because nobody's gonna understand what you mean by that. And then they had no safety, so they could have been doing whatever. They don't know what they're doing. And so yeah.
And there's no material list here, which I think makes it really hard for people who are not familiar with the lab to even like understand what they're kind of dealing with until they get into some of the like analysis in the trial. And something else that it kind of bothered me is in here the grams they use in the reactants. They're both very off from each other, but they don't state like what they're trying to aim for. They don't even say it. We have to assume it's 5 grams of the reactants, but that's not stated anywhere. And since they're both skewed so off from 5, it's just kind of confusing to come to that conclusion.
All right, and then going down to the conclusion and the error analysis. Basically, in their error analysis, there wasn't really that much of one. They said
What is it? The piffle. Oh,
I don't know if you agree with that, but they said I think we spilled some of the mixture after we measured, and like one of the scales may have been a little bit off, but they're not very specific at all. And they're like, yeah, like we may have spilled some, and may have gotten rid of some that we needed, but so yeah, and there's no math in it. There's no calculations as to what their error could have been. So yeah, incredibly vague.
The conclusion as a whole didn't expand on anything on how what they were calculating and how it applied to chemistry. So it was just a sentence that said the results, and it didn't really back anything up.
And then for atom economy, we got 68.34%. And like overall greenness, we thought that they used like over 10 grams of the sodium bicarbonate, and we thought they could that wasn't necessary, and they could reduce that number because they can still figure out the mass ratio with the smaller amount of greens.
And one thing that they did do good is I feel like they organized their thoughts and everything pretty well, but they just didn't have everything that they needed to make a good lab report.
Alright, let's see. Calculations, here we go. So this is, I believe this is trial one. No, this is trial one still. So we see this variable here. So I don't know what they're trying to do. Since you can just put the mass or whatever you measured, this should have been 3.05. So overall, as we keep going, we notice this is normal stoic. Yes, they got that right. Keep going, and then now here we go. We don't know what they're trying to do here. This is more variables, so just one thing saying. And then, but since we have their original mass before the heating, and then minus whatever that's supposed to mean, this is we don't really know where it's trying to lead to. So they shouldn't have just not done this in general. And then when we keep going, instead of rearranging algebraically, we understood where we get this first 0.639 since it's just all this expanded or condensed down. But then we get to that little parentheses. Now it says 4.473 grams, which is there, minus 1x. I don't know where they got the 1x.
I'm gonna better about it. They did it really fancy, but it's the 3.57 grams is your final that you guys said you originally started with in trial one, and they are basically saying x grams is equivalent to x grams from sodium bicarbonate to sodium carbonate. Though that may not be correct, they're assuming it's a 1-to-1 ratio, but I think what they did is assume it was a 1-to-1 gram ratio, not a 1-to-1 mole ratio.
Well, adding on to that, since we didn't know what that actually meant, we just had to assume a lot of things. Since there's just little 2-word subheadings after each one. And then now the solve for x. This should be fine. And then trial 2, they basically do the same thing, but again, they have the whole variables which helps that trips up our math. And then they average it, which should be fine.
Alright, yay! I'm going to comment on two, so I think Nick was saying there are 2 trials provided very different data. However, it should theoretically not matter how much we start with. I can start with 1 gram for trial 1 and then 5 grams for trial 2 and take that to the end to then do the percent calculations. But if we want to try to see mistakes, it's very easy to do that when your trials are close than if they're far apart, in terms of replication. We always want to try to replicate the best we can. And then, I don't know if you said the spillage part. They mentioned the spillage, but then they didn't say that caused air analysis to skew high or low. You have to talk about the directional nature of it, not to say, hey, I spilled something, sorry, right? You know, talk about why that isn't mattering in terms of the grand scheme of things. So, good job, guys. Last group, let's go.
Okay, so the first thing you notice is that the materials and the procedures is just kind of vague. It does give you a kind of a feeling for what you have to do, but it doesn't go in detail. They forgot crucible tongs, which you need to move the crucible. They forgot a desiccator, which you need to cool the crucible. They didn't have the clay triangle, so they just forgot a lot of materials. And then the procedure, they just said measure the initial mass of the mixture. They didn't say that you had to clean it before, use chem wipes, heat, clean. They just kind of left that really vague.
And to add on to that, the procedures they make sense for someone who knows what the lab is about and what the goal of the lab is, but if somebody was trying to repeat this lab and they didn't have an experience with the methods that we were using, they wouldn't be able to replicate it with success probably.
Also, replicating, a lot of science is replicating the same labs, just build off of what other scientists have already done. And in terms of using heat and fire, we're going to see fire. We don't know like in terms of safety, another scientist would not know how to approach this in order to do it safely and get like the same results.
Okay, and for the math, you just go on. So they explained what they were about to do very well. Like they showed you everything they were going to do, even though they did it somewhat backwards of what we did. It was easy to follow. So they figured out the mass of the H2O and CO2 produced, so the carbonic acid, and they found a percentage of what they theoretically thought that the sodium bicarbonate should be, and then they just set a proportion and solved it, and it's pretty simple and straightforward.
But they did forget a lot of units. Like they didn't have like that was supposed to be grams or anything. They just left it.
Yeah.
So when we're like talking about the data, I think personally that they did pretty well because they did 3 trials, and you can also tell like towards the end they reached their goal because you can see the difference for I think, well the first one there's actually no difference, and then the second one there's 0.001, so they accomplished like getting the constant mass that they want. So I think that they did like more than 2 trials. Yeah, they did 3 trials, so that was good.
So then for atom economy, so using the formula that they gave us, it should be so the mass of Na2CO3, so that was 106 essentially, over the total reactants, which is 63.08%, which should be theoretically, but I also like checked, so like what should be left after heating should be what they want, and then over starting, so that should be the total mass of reactants. So what I actually got for each of the trials, the first one that had a 69, about a 69.7%, and then for the second trial, they also had a 69.3, so they're very close. So whatever the process was, it became like similar results each time.
We said for the greenness of the lab, they minimized the amount of steps that they had, so they did 2 trials and then they just averaged them.
As for the conclusion, well, first they didn't have any error analysis, so we didn't know what they possibly did wrong, or what they could fix, or how the data could have been affected. But the conclusion is also really weak. They just simply restated what they got, and then they said that they can't really say the accuracy because they don't know the original, they don't know the true percent composition. It was just really like an overall weak conclusion. It didn't really say anything about what they learned or any principles that they applied. It just really restated the data that we already saw.
So probably the most coherent part of this was the math, because that's what they explained to us.
Nice, you guys talk about weaknesses and their strengths, awesome. Yay! So one thing off here is that, yeah, you're right, they just restated their data, and in terms of what they reported out, 82%, 83%, super close. They could have mentioned the error to be like, if there were error, systematic error, meaning the scale or something was skewed high or skewed low based on what they're looking at. In terms of what other information they could have included, their calculations were strong, it was fine. They could say, like, theoretically, they could run a third trial. So they did run 1 trial and 2 trials, but they heated it 3 times. They could run a third trial to then say, if they got consistent with that, then that should be approximately the true percentage. Okay? So we did all this, one, so that you're aware kind of like how to critique yourself and self-reflect as you guys go. Your conclusion for this should be a paragraph, not a sentence, right? This one actually, this lab has probably 3 to 5 main things you should be talking about in your conclusion. Your error analysis, you guys can talk about this skewing up or down based on the fact that I think it's 85%, remember? To show that map there. If you're trying to show math in Google Docs, you can use an equation editor. You insert, and it's a little tricky sometimes, but it's worth it if you guys can learn that, because then you're not trying to take pictures of your work and then importing it into your documents, but it's fine if that's what you've got to do for a while, okay? So any questions on this lab right now? Okay, so we have right at 30 minutes left. No, let me make sure. Okay, we get at 10:10. No, 8:37. 8:37. So we right at 10:10. We get out in about 30 minutes. So you guys can either choose to focus on multiple choice. If you have your textbook, the back of the chapter of each chapter 1, 2, and 3 has a self-assessment. I usually require people to do it, but it's up to you. I think you should do those 15. There's 15 questions per chapter, and there's an answer key provided in there. And I'm here if you want to talk to me today. I can stay a little after school for you guys today, and I'm certainly staying after school tomorrow for you guys. Okay? If you want to work on unit review, you guys know where that is in your packet. it's like next to the mass spec work, okay? You can do that, or if you just want to finish your lab with your lab group because you have everybody here today, do it, okay? Here's what I did.